I did, as promised, get the test graded, but, well, here's the thing. I don't like to give you back the scores without giving you back the test so you can see how that score came about, but it looks like it won't be until Thursday when I can get the last test completed, which means I don't want to pass out the test until then. So would you prefer to get your scores now and then see the test on Thursday?
Yes, get your scores now.
Okay, so after class, I will go ahead and upload the scores to Moodle so you can see your scores. And at a later date, we will upload and return the test so you can see those as well. Okay, with that over, we're going to, it seems like, change topics completely initially. We're going to talk about rotational motion. But the reason we're talking about rotational motion right here is so we can get back to forces, adding another type of acceleration. So rotational motion, we see rotational motion all the time. Let's see, the next slide has an example for a Formula One. Come on, go away. A Formula One racer, and talks about the cars go around a track. Of course, NASCAR would be your ideal example of just, turn left, turn left, turn left, turn left, going in a rotation, and the tires are rotating. And I think we all understand we see rotational motion all the time. Right, I've got a turning platform here so I can illustrate rotational motion in a minute. Why would we treat rotational motion in any way different than linear motion? Well, the answer is really simple. In rotational motion, if you have a rigid object such as that platform, then everything is staying fixed with respect to the rest of it. That is, as an example, this little notch is staying with the same spatial relationship to this screw hole no matter where it is. It's just going around, but the relationship stays the same. But that means that it takes the same time to do a complete circle whether you're near the center of the circle or whether you're far from the circle. But of course, we've all learned the circumference of a circle is 2 pi times the radius. So that means the circumference is bigger when you're farther away, smaller when you're closer. But speed is equal to the change in position over the change in time. So if it's going in a circle, that's equal to the circumference divided by what we call the period. The period is the time to complete one cycle. So circumference, we know circumference, like I said, is 2 pi times the radius over the period is the speed. The period is the same regardless of where you are in that rigid object. So what happens to the speed as you move a farther distance, a bigger radius from the center of rotation? What happens to the speed, the v there, as the radius, the distance from the center of rotation increases? The speed increases linearly. They all have the same period. They all have the same time to do the circle, but the speed differs with location. And so when we talk about rotational motion, we often don't talk about the speed. We talk about the angular speed. Angular speed is defined as the change in angle divided by change in time. Now, what did I use here to indicate angle? That's the Greek lowercase th, theta. That is our go-to symbol to indicate angles. And so that's omega. That's actually the letter the student told me I had wrong was omega. That's a lowercase omega. A lot of students say W, and I always correct them because that's not a W. It's the omega. Christ is the alpha and the omega. Omega being the last letter of the alphabet, alpha being the first. And we're going to use alpha and omega here. Alpha will be our angular acceleration. Omega will be our angular speed. So angular speed is the change in angle divided by change in time. Now, I already went off on a wild tangent to tell you about degrees and why we have 360 degrees in a circle. But degrees are, a contrived angle measurement. They don't have any fundamental reason for using them other than the time it takes for the Earth to orbit the sun is close to 360 days. It's the only reason to have degrees. But it turns out that there is a really good reason to have the unit that we call the radian. So we're probably familiar with radians. Here's a really simple question. How many radians are in a circle? 2 pi. Why? The answer is because we have a simple relationship between the angle and the arc length. So here we have in green the arc length. The arc is part of the perimeter for a given angle. So that arc length, the curve, is proportional to the radius of the circle and the angle such that, and I usually write this equation this way, the arc length is equal to the radius multiplied by the angle. That's the true relationship that defines really what a radian is. Because if you take that and you solve it as was done just below the equation I put in the box, the angle is the arc length divided by the radius. And pi is simply a defined relationship between the circumference and the diameter of a circle. You know that circumference, I just wrote as 2 pi r, or pi times diameter. Pi is simply defined as the ratio of the circumference of a circle to its diameter. And of course, it has been determined that pi is irrational. What does it mean for something to be irrational? And of course, we're not talking about people. I'm not saying, Corso, you're a Chelsea fan? That's irrational, right? That would true statement, right? But
let's not start. Let's not start.
Chelsea has won Premier League 2 out of the last 3 years. It really makes me sad. On the other hand, it makes Corso very happy. But in math, when we talk about something that's rational, that means it can be expressed as the ratio of 2 whole numbers. Irrational can't be. And pi is like that. It can't be expressed as the ratio of 2 whole numbers. And, you can memorize hundreds of digits if you like, thousands, millions. It never ends because it's irrational. So pi's definition is based on circumference and diameter. And using that relationship, we can define then delta S is r delta theta, or delta theta is delta S over r. For a complete circle, that's kind of complete. The arc length for a complete circle is equal to the circumference is 2 pi radius. And so delta theta for a complete circle is 2 pi r over r is 2 pi. So that's why there are 2 pi radians in a circle. Now here's something really important. What are the units there of my angle? If delta theta is delta S over r, S being the arc length, it has units of meters, distance. What are the units for radius? Meters. So what's meters divided by meters? They cancel. It's unitless. So radians are actually unitless. We use the word radian to remind us we're using the unitless, the natural angle. Radians are the natural angle. If we use degrees, we've just used a conversion factor from the unitless angle to something else. Well, how do you convert? This is your key. One circle is 2 pi radians, or 360 degrees. Remember, conversion factors are always equal to 1. So if I need to convert, let's say, 45 degrees into radians, I need a conversion factor that has the unit I want on top and the unit I'm trying to get rid of on bottom. And I need to find some fraction that's equal to 1. Well, just looking at the relationship in the red box, since 2 pi radians equals 360 degrees, then if I divide both sides by 360 degrees, 360 degrees over 360 degrees is most clearly 1. So that's my conversion factor. And now I'll erase the word degree and put the degree sign. And of course, most of us are really astute, and we know that we could cancel a 2 there and make it pi over 180 degrees. And of course, 45 divided by 180 is 1/4. So 45 degrees is pi over 4 radians. When I use pi over 4 radians, that radians might magically disappear. Why is it fine for it to magically disappear? Because it's unitless. Radians is unitless. If you have degrees, the degrees can't magically disappear because you have to use a conversion factor to get it to radians, and then it can disappear. Okay, so this equation, the arc length is equal to radius over delta pi, is pretty important. That's what's going to allow us to relate the distance something travels as it's moving in a circle with the amount of angle that it rotated through. And so, well, this here is just showing how the distance varies with radius, which means also the speed varies with radius, because speed is distance over time. So here is our relationship between speed and omega. Remember I said omega is equal to the change in angle over change in time. That's its definition. But if the change in angle is going to be, I got to go up 2 slides to remind you, change in angle is delta S over R. Then I can rewrite this as, but what do we call delta S over delta T? S being the distance it's traveled. Not the radius, the distance it's traveled. Something's traveling, the distance it traveled, delta S, divided by time, is the speed. Or velocity if I had direction. So this is equal to the speed divided by the radius. So if you just multiply both sides by radius, you get speed is equal to radius times angular velocity. So there's a very simple relationship. The speed is angular, wow, beautiful writing. Angular velocity times radius. We had the distance that it travels was equal to the angle times radius. We're going to go one step further and talk about acceleration, but it turns out acceleration is going to have 2 pieces. Why would acceleration have 2 pieces? What's the definition of acceleration? Okay, if it was change in speed over change in time, I would only have 1 to worry about. But it's change in velocity. It has both speed and direction. And so we're going to have 2 parts to our acceleration, one for the change in direction and one for the change in speed. The change in speed part we call the angular acceleration. The angular acceleration then is defined as angular acceleration alpha is the change in angular velocity over change in time. Right? Just like acceleration, change in speed over change in time, change in angular speed over change in time. And so alpha is I put a subscript on the acceleration. I put T for tangential. Tangential is a new word, probably. Tangential means in the direction that it's moving. Technically, it's tangent to the path. Tangent to the path means in the same direction as the path. So the tangential acceleration is the acceleration in the direction it's traveling, the part that relates to the change in speed. So the angular acceleration relates to the tangential acceleration, or solving this for A. So if you look at these equations that are in boxes, what do they all have in common? They're what? It sounded like you said they're easy. They all have the same last thing. What's that? The radius. They all are just the angular thing multiplied by radius gives me the linear motion, which makes a really easy step for us, the kinematic equations. If I take all of my variables and multiply them by the same number, I'll have the same equation, right? It's equivalent. And so all of our kinematic equations work out to be exactly what we did before, but changing from what we call the translational, translation is moving it along, motion to the rotational motion. So if we look at our kinematic equations, we had that equation. If we substitute, we'd have same equation, I just changed x's to thetas, v to omega, and a to alpha. And likewise for the rest of them. I should really change color here. That becomes so I really don't spend the time doing these problems because you've already done these problems. It's just using the same equation but variables that are different names. So if you could do it before, you could do it now. You could do it before, right? Yeah, sure you could. I said there's the directional part. As you go around a circle, the direction you're traveling is constantly changing. Going a circle, constantly changing. We talk about an angular velocity. Somebody used the term angular velocity for omega. And indeed, we often call it the angular velocity. Remember, the difference in velocity and speed is direction. So how could we define a direction for the angular velocity if it's constantly changing directions? We don't want to say, oh, it's constantly changing direction. That's just not convenient for our calculations. So can you find a relationship to that rotational motion that's always going to be the same? You have an answer? Well, physicists have. And so has Gila. Go ahead, tell them, Gila. Pretty sure you know. No. Okay, does not want to be on the spot. Well, there are two directions that would be consistent with rotational motion. One is in the case of, well, that record coming out of the screen towards you, and the other would be going into the screen away from you. And so scientists have settled on what we call a right-hand rule. And you already have some knowledge of the right-hand rule. You probably don't know it. How many people have taken organic chemistry? Okay? You talk, that's pretty much everyone. I'm sure there's a couple that haven't, but you talk about things like isomers and structural isomers, chirality, all these kinds of things. And so you have things like S and R forms of the same chemical. The R stands for recto or right, and the S stands for sinister or left. So the R is following the right-hand rule, the S is following the left-hand rule. How many people knew that sinistrality means left-handed? 3, 4. Not very many. I have a cousin who's left-handed. He loves to wear a shirt that says sinistrality is not a 4-letter word. Because, of course, left is a 4-letter word. So, we use the right-hand rule, and so this is our first example of the right-hand rule. And we're going to have more examples of the right-hand rule. I think we'll have 4 by the time we finish second semester. So the first example is for rotation. For rotation, you take your right hand, and of course it's really important not to use your left hand. Back when I was in college, I had a student, the teacher's doing this, I asked a classmate. The teacher's doing this, and he's using his left hand. And the teacher says, Saeed, you have to use your right hand. He says, but I'm left-handed. It really doesn't matter, because it's a standard based on the right hand, not based on you. Furthermore, if you're left-handed, the right-hand rule is easier because you can write while you're sitting there using your hand to figure out directions. So with this first right-hand rule, you take your right hand and you wrap your fingers in the same direction that the rotation is going. So using the picture behind me, the rotation is going clockwise, and so I wrap my fingers so they are going clockwise. And then my thumb points the direction we identified for the angular velocity. So in that picture, the angular velocity is straight into the screen. Or if you look at a clock, the angular velocity for the second hand, if we were to assume that this was a smooth moving second hand and not a click, 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 the angular velocity would be like that into it. Now here's another thing to think about. When it comes test time and you have a question that requires you to use the right-hand rule, you know what big advantage you have there? Your paper can move. You don't need to sit here and get yourself all twisted up to try to get your hand bent in the right direction. Just rotate the paper to make it easy, okay? I mean, I know I have a tendency to try to be very rigid with it. It's that direction, I have to do it that direction. But if you rotate the paper, you can take away some of the contortion. So the right-hand rule, clockwise, was into the clock. And we call into the clock the negative direction. So it turns out that clockwise is negative. And so if you define x's out, that would be negative x. If you're doing one-dimensional rotation, you're like, what in the world would one-dimensional rotation mean? One-dimensional rotation means that you have rotation that is all in one plane. So the direction is that way or that way. For one-dimensional rotation, clockwise is negative, counterclockwise is positive. And that's based on what rule? Right-hand rule. Okay, and so yes, there I have it. Right-hand rule, clockwise into the screen. How does that relate to my acceleration? I said my acceleration had both a speed part and a direction part. So if it's going at a constant speed in a circle, then its angular acceleration is 0 because the rotational speed is not changing. But something that's going in the circle has its direction constantly changing. Now this picture is showing a finite change in position. Why a finite? Because we can't show you an infinitesimal. It didn't move. So if you have something moving from position 1 to position 2, the velocity changed from like this to like this. And so the change in velocity is the direction of the acceleration. And that change in velocity, in this picture, you can see, well, that's not toward the center. But if we were to make it a smaller and smaller amount of time between them, it would be closer and closer. So that it turns out, if you do infinitesimal, i.e. if you just do the calculation, you find that the direction for the acceleration when it's going in a circle is toward the center, and we call that centripetal. So centripetal means toward the center curvature. So for something to go in a circle, it has to have an acceleration toward the center. So if I put that on there, is that mass accelerating? Yes. What direction is accelerating? It's what? I think the word you're trying to say was tangent. But no, it's going at a constant tangent speed. But its direction is changing. Well, it's supposed to be. There's supposed to be no friction here. But the direction is constantly changing, so there's an acceleration toward the center to make its direction change. And so that's what we call a centripetal acceleration. Now that brings out the confusion between centripetal and centrifugal. So centripetal toward center. Centrifugal is away from center. Now I'm going to talk about centrifuge in just a moment, and we'll have some confusing words. But centripetal is toward the center. And for something to go in a circle, it has to have an acceleration toward the center. And so we call the acceleration toward the center necessary to go in a circle. Is centripetal acceleration. So, of course, we're going to have to determine what the centripetal acceleration is, but first we'll have a clicker question. What direction must you accelerate to maintain a circular path at a constant speed?
I'm not able to log into the.
Did you get yours straightened out, Cole? Wasn't you that had a problem last time?
I'm pressing a number.
Okay, so Ashley's working on it, and Leslie. What is it doing?
Change channels. It's on 30 from Oakham, and it won't change to 33.
I've never actually used one of these. No, that doesn't look right. I don't know enough about this to figure it out.
It's not linked up to the channel. It says
I don't know enough about that to know. Okay, moving on. The answers we got were one person said parallel to the path at all points. 26 said toward the center. Nobody said away from the center. And one person said there is no acceleration in constant circular motion. So, Edward, hey, I pulled yours out on Friday, but obviously you weren't here. Tell us about this.
Well, I did PV, and the reason is because anytime you change direction direction, there is an acceleration. And if you're going in a circle, you're obviously turning, so there has to be an acceleration. In this case, it's toward the center of the circle.
Okay, now let me ask you a couple more questions. What would happen if you had an acceleration parallel to the path? You'd go faster in the same direction. So that's why that one's wrong, because that would make you go faster. What would happen if there was no acceleration?
Well, straight, I guess.
You would have constant motion, not constant circular motion, but constant motion. That is same direction and same speed. But we're not doing constant motion, we're doing constant circular motion, so that's why this one here was incorrect. And then nobody said away from the center of the circle, so I won't worry about that. Okay, so what is the centripetal acceleration? Well, through calculus we find, that the centripetal acceleration is the speed squared divided by the radius. Or since speed is v is omega r, you can put that in and you'd have omega squared r squared over r, or omega squared r. So the acceleration necessary to go in a circle, that's what centripetal acceleration is. The acceleration necessary to go in a circle is the speed squared divided by the radius. Which means we have just some very easy relationships. If I take this little bob and I swing it around my head, how is the acceleration now when it's going relatively slowly compared to the acceleration now when it's going much faster? I'm not going to hit my head.
Way bigger.
It's way bigger when it's going faster. Because if you, for instance, double the speed to keep the radius the same, you're squaring the speed, that would be 4 times the radius. Now, what about changing the radius? What if okay, so I got it knotted by accident here. It's got a smaller radius. If I were to go the same speed with the smaller radius, what is that doing to the acceleration? Well, I'm trying to keep the speed the same. It will decrease the acceleration. So the acceleration depends on both. I don't know how. There we go. We got that. Now, since I have this out, let's do a few more things. You guys know that until I was 5, I grew up in Africa, right? Lived in Liberia, Sierra Leone for 2 years, Liberia for 3 years. And out there in Liberia, where I actually have some memories, and I remember my playmates, they had rice fields, and they would set up cans around the rice fields instead of scarecrows. And when there was a bird, then the lady out there caring for the field takes her slingshot, and she goes, and she throws a stone, much like David with Goliath, and hit that can and scare the birds away. They're really good with that slingshot. So, of course, as a kid, I was really enamored by the slingshot, so we got a slingshot. They just made them out of, we call it raffia. It's made out of the fibers and long leaves. And I'd go around playing with my slingshot. So I used to think I was pretty good. Now, not very good now. This isn't a slingshot anyway. But with the slingshot, let's do a wrong version of slingshot. I'm swinging this around the circle. It has an acceleration. What's making that acceleration? What did you say, Alex? Okay, the string. The string is supplying a force, because if you're going to have an acceleration, you have to have a force to cause it, right? Newton's second law, the acceleration is the net force divided by the radius. Now, is it just the string acting out when it's going around a circle? No. Now, we are going to ignore the air resistance, but what else is acting on it besides the string and the air resistance we're ignoring? Gravity. Gravity's acting downward. What direction is the acceleration, or is the force of tension? Okay, it's in the direction the string is going. If the string is perfectly horizontal and gravity is perfectly vertical, what's going to happen to the motion of the bob? Okay, the bob is going to have to drop because gravity is pulling down, nothing's pulling up. But as soon as it drops, then the tension is partially upward, and so the tension is lifting as well as pulling in toward the center. And if I go faster, it's going to be flatter because the acceleration necessary to go in a circle goes up as it goes faster, which means the tension, the force from tension toward the center has to go up, so the tension goes up, has to be flatter, so the force vertical stays the same. Now, back to the slingshot. Let's imagine now that I'm going to cut the string, which in my case is going to be to let go of it. And just for grins, let's say that I want to try to hit Irving. So if I want to try to hit Irving, when should I release the string? Okay, instead of saying now, at what position should I release the string?
On your right side. I think its velocity is in the direction.
Okay, when its velocity is going toward Irving. So it's going in a circle. In this position, what direction was its velocity? That would be directly away from Irving. Here, what direction? All right. What about here? And here? Toward Irving. So I need to let go. Right now, it's never going to work. I need to let go when it's right here. Now, we should all be pretty confident that I won't be able to time this right. Right? Especially when you're using a slingshot, you do more than just go in a circle and let go. Right? You do the whole, that kind of action, which helps you aim better. But I will try to do this correctly. So I will try to release it when it's here. So yeah, do be aware. Okay, don't let it hit you. Okay, so what did I do wrong? I released it too late, right? You have to release it at the right time. But once it leaves, yeah, toss it. Once it leaves my hand, what direction will its path, or what shape will its path have? Okay. Okay, it would go straight in the XY plane, in the horizontal plane, and the vertical plane, it's a trajectory, so it's going to be falling. Right, so we know how to treat that, and we know that when I let go, it's going to go in a straight line from the point I release it with the velocity it had at that moment. So we're going to do a few problems to work on this using this centripetal acceleration. Now this equation right below it, sum of the forces, subscript C. That subscript C means in the centripetal or toward the center, in the centripetal direction or toward the center. So the sum of the forces toward the center, according to Newton's second law, is equal to the mass times the acceleration toward the center. We have a name for the sum of the forces toward the center. The sum of the forces toward the center we call the centripetal force. But the centripetal force is not a force that acts on an object. What is it according to that equation? It's a sum of the forces, a net force acting on the body. So when you make a free body diagram, what forces do you put on the free body diagram? By definition, what forces do you put on? All of the forces that are acting on the body. Well, the centripetal force is not a force acting on the body. It's the sum of the forces acting on the body toward the center. So you never, ever, ever, ever put the centripetal force on your free body diagram. Because it's not actually a force acting on it. It's the sum of the forces in a direction. So it's a mistake that people make over and over, which is why I said never, never, never so many times. Okay, here's a picture with some confusing words to try to explain how a centrifuge works. A centrifuge, you probably know, you go to chemistry lab and you need to separate things. You spin it up and things separate. More dense things go to the outside, less dense things go to the inside. How does it work? Well, we use bad words like centrifugal. Centrifugal means away from the center. What really makes a centrifuge work is inertia. You spin something around a circle, and inertia the idea of Newton's first law is the idea that things have a natural tendency to go in a straight path, and a force has to act on them to make them deviate from that straight path. So when you have something like this going around a circle, naturally, that mass is wanting to go in a straight line, but there has to be a force making it change direction. What do we call that force? Okay, and this is where students get confused about the terminology. The force that's making it change direction, the one that's going to show up on our free body diagram, is the force of friction. And then we would add up all the forces toward the center, and we would only have one. And so we'd say the sum of the forces toward the center is the centripetal force. And so the centripetal force turns out to be caused by the force of friction. The force of friction is the actual force that's doing it. So if I speed this up, I probably shouldn't do it with the mass that heavy. Let's do it with the stopper, much less damage. If I speed this up, what happens if I go too fast? It flies off. Why? Because the force of friction wasn't large enough to supply the acceleration necessary for it to stay in a circle. And so it slid off of that circle and came off. Now, the same thing occurs in your centrifuge. You have the material that's going in a circle. Okay, should slow it down first. Going in a circle, and it is trying to go straight, but the material, whatever is in your test tube in this picture, is pushing in a circle. But if I have something that's more dense, it has more mass per volume, more inertia per volume, it's going to require more force to make it deviate, and it will push its way out to the end. Because inertia is trying to make it go straight, and you have to have the external force from whatever goo is in there to make it change directions. So this has the word centrifugal force. I put quotes around the force because we call centrifugal force a fictitious force. Fictitious because it doesn't really exist. There is no such thing as centrifugal force. But if you yourself were inside of the centrifuge, let's say you're at an amusement park and you're inside one of those rides that spin, you think of yourself as stationary. Right? My arm's right here. It's not flying around. And because you think of yourself as stationary, you've put yourself in what we call a non-inertial reference frame. Non-inertial reference frame means a frame where Newton's first law doesn't apply because the reference frame itself is accelerating. If you're going around the circle, you are accelerating. If you say, my reference frame is stationary while it's accelerating, that's non-inertial. And in that reference frame, in a non-inertial reference frame, you actually have to have a force to stay put. And so that's where you have the centrifugal force becoming real. Inertial force, likewise, is fictitious. Inertia is not a force, it's what things do. But if you're in that non-inertial reference frame, it appears that what things do looks like there's a force acting. So in reality, why does the centrifuge move more dense materials to the outer portion of the spinning tube? Trace will get his exercise. Have me put in whatever answer I want?
No, it's just correct answers.
Oh, just the correct ones. Okay. I see you got it working. That's good. Okay, we still have James and Irvin. It didn't take yours, Irvin. I know you got up and walked. I saw you. Yeah, just walk on up. Come on up to the front, Irving. Too bad we're not doing fun demonstrations. We'd have you do it. Come on, clicker. Nope. Nope. You got to put new batteries in soon. I still got nothing, man. Okay, well, we do have to go on. Well, not sure what's going wrong there. 17.7.4. We did not have complete buy-in to what I said. Amanda, you are next on. You're the next contestant on Price is Right, yes. Tell us what you think.
So I put inertia.
Okay, why'd you do that?
Like it says, they're just gonna push it towards like the outside. They're trying to go in a straight line, but it's preventing them. And so then we'll be pushed to the outside of the walls.
Okay, very good. Inertia, now she said push. In your reference frame, it feels like it's pushing. Like when you're in the car and going around the corner and your sister's between you and the outside window, you're being pushed into her, right? It has nothing to do with your feet pushing, right? Yeah, true. Your sister deserved it for being next to the window when you had to sit in the center. So inertia is the property of you going in the straight path unless something pushes on you. And so if we had vinyl seats in our station wagon, okay? So you're sitting on that vinyl seat, you don't have much friction. You go around a corner, you do slide into your sister. And it's because your inertia is trying to keep you in a straight line while the car is turning underneath you. Same idea here. The inertia is trying to keep things in a straight path. Okay, so let's look at a problem. We only have 3 minutes, so we'll have to stop with this. Modern roller coasters have vertical loops like the one shown in the figure. The radius of curvature is smaller at the top than the sides, so that the downward centripetal acceleration at the top will be greater. Remember, centripetal acceleration is v squared over r, so they make it so it's a smaller radius of curvature at the top, so you have a bigger acceleration necessary to stay in a circle for the same speed. Keeping the passengers pressed firmly into their seats. What is the speed of the roller coaster in meters per second at the top of the loop if the radius of curvature is 14 meters and the downward acceleration of the car is 1.6 g? Okay, I'll put it as y, and then we'll write it differently. Remember g, what is g? 9.8 meters per second squared. So now I'm going to look at somebody in the roller coaster. If you're any kind of sport, you've got your hands up, right? So you're sitting there in the roller coaster. What forces are acting on you at the top of the roller coaster? Gravity, which points? Down. So I have force of gravity equals mg down. What else is acting on you? The normal force. You have a force normal. Notice I made a force normal downward because you are firmly pressed into that seat. The seat is trying to keep you from going up into it. Normal force is pushing you down. Those are the only two forces. Now, when you look at that, does it make you a little worried? I mean, what direction is your net force? Downward. If your net force is downward, it seems like you have a problem. You're going to accelerate in what direction? Downward. Right, you're going to accelerate downward. And so you're like, uh-oh. If I accelerate downward, I fall out of my seat, don't I? Not exactly. Because the cart is traveling horizontal, which means that you are traveling horizontally as well. And if there was no cart, what path would you take? You would take a horizontal path that starts falling. So if you're here on the roller coaster and there was no track, my finger moved the screen while I was trying to do that. You would take a path like this. Well, that path didn't curve as much as the track did. So your falling motion would make you have to go through the cart.
Is it going the opposite direction?
Oh, yes, you're right. I didn't look at those arrows. So that's the path you would take. Thank you. So you would have to fall through the cart. The normal force is keeping you from falling through the cart like you would if you were just to fall. Oh, goodness, I'm out of time. I will finish this up at the beginning of next class period because we got